The Advanced Land Transportation Performance Simulation, known as ALPS, has been developed by Kimley-Horn and Associates to study the operational performance of complex multimodal environments. ALPS is a holistic model, allowing the analyst to study mobility of persons and goods through a variety of transportation modes. ALPS models how people depart from their origins and arrive at their destination through a combination of walking, driving, and riding in a variety of transit systems. ALPS can be used for a wide range of planning and operational studies for regional corridors, urban developments, activity centers and campuses, intermodal terminals, and landside airport operations. ALPS can be applied to preliminary engineering, design, and operational management. The following tour of ALPS project examples shows the broad range of applications that ALPS has been applied to. The flexibility of the people-based modeling platform allows the analysis of operational challenges from regional evacuation management to campus transit circulators. ALPS was used to study the complete multimodal environment surrounding the Minnesota Twins baseball park in downtown Minneapolis. Working as part of the design team, Kimley-Horn analyzed alternative pedestrian facilities for stadium egress. Multiple options were tested under operational scenarios with up to 60,000 pedestrians exiting the baseball stadium and the basketball and hockey venues within a short period of time. The ALPS simulations showed the benefits to pedestrians and street traffic of the proposed pedestrian sky bridges, as well as the comparative impacts of alternative strategies for parking and light rail platform location. ALPS is especially suited for modeling of intermodal transit stations where pedestrians, transit, and vehicles interact. At the time that the Northeast Corridor Station near Newark Liberty International Airport was being designed, ALPS was used to predict the pedestrian movements and potential congestion areas in the planned future station for the Port Authority of New York and New Jersey. At this intermodal station, air passengers connect to the Newark Air Train People Mover to be transported to the airport terminal. ALPS tracks each person or group of people traveling together, on the train, on the People Mover, and walking through the terminal to their gate. ALPS continuously collects data as people walk through the terminal at speeds determined by their demographic characteristics. ALPS models are also being used to predict performance of future concepts for high-speed rail intermodal stations. ALPS can be used to understand the scale of a given station's required footprint, the size of ground transportation facilities, and the capacity of the transit systems that would be needed to adequately serve the passengers at each future station. Using a supply-side analysis, as in this example, a schedule of trains and associated ridership is used in ALPS to estimate the distribution of passengers arriving and departing the station by various ground transportation modes, such as private vehicles, taxis, pedestrian systems, circulator buses, and light rail transit. The features in ALPS for schedule-based multimodal demand and supply simulation have recently been applied to large campus environments. ALPS was used to simulate and assess an advanced technology transit system at the Cal State Fresno University campus. The circulator system would carry students across campus, to and from remote parking, and into adjacent urban developments. Using ALPS, over 100 small vehicles are simulated operating in a demand response mode. This scenario study modeled a complex moving block control system which scheduled the vehicles in response to the passenger demands throughout the school day to minimize the travel times of each individual trip. ALPS models the complete class schedule to generate the person trips throughout the day. Pedestrians place requests for transit vehicles to transport them to a specific destination, such as a parking lot or the student's next class. ALPS is used to evaluate the efficiencies gained by ride-sharing by filling as many of the 4-passenger vehicles as possible when travelers are bound for a common destination. ALPS modeling is based on standard principles of trip distribution and travel path assignment. ALPS calculates the trip distribution between all origin and destination points. When a class change occurs, the students walk to their next class or to a nearby transit station. Those that utilize the network of transit stations will likely have longer trips, such as traveling across campus to the stadium or to remote parking. ALPS calculates the travel times and costs for each alternative path, and then assigns each traveler to a path and an associated mode based on a logit algorithm. ALPS models have been used to study dense urban settings. A model of downtown Houston was recently prepared in ALPS as part of the preliminary engineering of a new light rail line. Results from ALPS were used by Metro to achieve approval of the project's environmental impact statement. The impacts on pedestrians and traffic at the point where this new line would cross and merge into the existing LRT line were shown to be minimal. ALPS was used to simulate streetcar operation of the new LRT line, where trains run in an active traffic lane. In the same simulation, the operation of trains along the original line used signal preemption and dedicated right-of-way. These two modes of train operation allow realistic comparative analysis of light rail train performance and operations for development scenarios 25 years into the future. Similar modeling was performed with ALPS to study bus, traffic, and pedestrian activity in downtown San Antonio. Two different bus operating scenarios are represented side by side in this video clip. The transit agency studied the density of pedestrian activity that would occur where their transit patrons must wait to board a specific transfer bus route. The current operations are shown on the left. In comparison, the right-hand clip shows the difference in the pedestrian activity when every passenger is able to board any bus to a planned downtown transfer center to make their connections. Including tourists and citizens, this ALPS simulation has over 165,000 pedestrian movements modeled throughout the 24-hour day. Using ALPS, a day's worth of simulation is executed on a typical Windows PC in just a few seconds. Several ALPS modeling projects have been completed for casinos in Las Vegas, including one of the newest at Las Vegas City Center. During the design phase of this project, ALPS was used to analyze the porte-cochere operation at the front entrance to the facility. This area accommodates valet parking, taxis and limos, and other shuttles and automobiles. This unusual configuration of multi-level roadways and roundabouts is easily simulated using ALPS. Various valet scenarios were tested to predict anticipated wait times, vehicle queues, and congestion during high-profile VIP events and popular times for tourists, such as New Year's Eve. ALPS has been used by more than 20 airports around the world for modeling and designing landside operations. The ALPS model shown in this clip is of the Humphrey Terminal at Minneapolis Airport. The model includes all passenger movements as they pass through ticketing, security, airside concourse, and baggage claim levels of the building. Tens of thousands of air passengers can be simulated for a 24-hour day in several seconds and can be played back as animation at any desirable rate of speed. Ticketing and other queue processing areas are modeled realistically using industry-standard probability distributions of processing times and queue dynamics. In this clip, groups of passengers traveling together are represented as different sizes of circles or clusters of passengers. ALPS can even simulate the operation of vertical circulation systems between building levels, including banks of elevators, escalators, and staircases. Security screening of air passengers is modeled in ALPS, including the queue lines, document checkpoints, baggage screening, metal detectors, and random checks. In baggage claim, ALPS models the effect of travel party size, including when travelers are joined by greeting visitors. The space modeled for each group also includes luggage, so the circles or clusters grow bigger as checked luggage is picked up from the belt. Even luggage carts are modeled for the travelers who choose this convenience. Evacuation planning is an important component of any facility design. ALPS can be used to simulate the evacuation of public buildings, airports, campuses, and even entire urban districts with modeling features designed specifically for this purpose. This clip shows an ALPS model of the evacuation of a large airport terminal. The pedestrians in the terminal are assigned likely evacuation paths for each part of the building, including the fact that some people may not follow directions. The modeler can then choose the time of day to trigger the evacuation event and collect detailed performance information on the resulting conditions. This example shows a case where passengers were directed to move quickly to the closest emergency exit. The passengers were moved out of the building to refuge areas around the aircraft parking positions on the apron. Shortly after, a fleet of buses is activated in ALPS to pick up passengers from each of the holding areas and transport them back to landside refuge on the other side of the airport. The simulation shows how difficult evacuation operations of large facilities can be. In this example, it takes over 2 hours to move all of the passengers and staff to refuge. Analysts can study a wide range of statistical data calculated by ALPS to answer important questions about how one strategy compares to another. In this example, an occupancy graph shows how long it took to clear the last holding area on the airside apron. The airport now knows that more buses need to be dispatched to highly used terminals should an evacuation plan need to be put into effect. Using ALPS, a wider range of variables and trade-offs can be studied, since simulation of tens and hundreds of thousands of pedestrian movements are processed extremely efficiently on typical Windows computers. Multiple scenarios are typically evaluated to compare the results of different evacuation strategies. ALPS makes this easy by allowing analysts to study combinations of transportation modes. In this example, an evacuation of a sports arena in an urban setting is being studied. The arena has a parking garage, remote parking facilities served by shuttle buses, and a light rail station. ALPS is first used to model normal operations. Then the evacuation event can be triggered at different times to analyze evacuation time and pedestrian densities in different parts of the site during the event. The ALPS simulation demonstrates that the shuttles experience the largest delays in the evacuation process. The exposure of these patrons waiting outside the building creates its own set of safety hazards. Here, the ALPS simulation shows that the building can be evacuated completely in 15 minutes, but it takes well over 1 hour to clear the site. The heavy traffic congestion created by the egress from the parking garage actually contributes to the delays in the shuttle bus operation. Alternative strategies can easily be studied by reconfiguring egress paths, the number of shuttles, and other variables. In this alternate scenario, ALPS is used to simulate how evacuated people, unable to reach their automobiles, were moved on foot to safe locations further away from the arena. This evacuation plan requires considerably more management as pedestrians stream away from the arena to reach designated areas of safety. In this video, we have demonstrated some applications of ALPS for analyzing multimodal planning and operations scenarios. ALPS is a powerful and unique tool for modeling how people depart from their origins and arrive at their destination through a combination of walking, driving, and riding in a variety of transit systems. ALPS has been engineered to process complex systems with hundreds of thousands of moving entities at impressive speeds without significant loss of fidelity. For more information on using and applying ALPS, please contact any Kimley-Horn staff.